Today is November 8th, 2025. In the world of national security, some events happen far from public view. They happen in the sky, over vast, empty stretches of ocean. One such event was a test known as Flight Test, Exo-Atmospheric Mission 02, FEM-02. At its core, the idea was straightforward. A target missile was launched. It was designed to mimic a threat. Then an interceptor was fired to stop it. The goal: hit a bullet with another bullet. We'll explain how this defense system is supposed to work, step by step. Then we'll show the facts, the hard data, that prove success or failure. This is a story of immense speed, precision, and the relentless pursuit of security. The importance of a test like FEM-02 cannot be overstated. Ballistic missiles represent a significant threat. They can travel enormous distances at incredible speeds. They can carry conventional or nuclear warheads. For decades, the only defense was the threat of retaliation. Missile defense systems offer a different possibility. They offer a chance to neutralize the threat before it reaches its target. But that promise depends on the technology. Tests like FEM-02 push that technology to its absolute limit. They ask one critical question: can this system actually protect us? The world watches these tests to see if the shield is real. Our strategy: first explain, then prove. To understand what happened in FEM-02, you first need to understand the pieces on the chessboard. A missile defense test is not a simple affair. It involves three critical elements, and each one must perform its job flawlessly. The first element is the target missile. This is not just any rocket. It is specifically designed and launched to replicate the flight characteristics of a potential adversary's ballistic missile. It acts as the enemy in this carefully scripted drama. Its launch marks the beginning of the test. Planners know its general flight path, but the defense system must find and track it on its own, as it would in a real-world scenario. The success of the entire test depends on this target performing as expected. The second major part of the test is the vast network of radars and sensors. These are the eyes and ears of the missile defense system. Powerful ground-based radars, sea-based sensors, space-based sensors are tasked with the initial detection. Once the target missile lifts off and clears the horizon, these radars send out powerful beams of energy. They listen for the faint echo that bounces off the target. This data tells the system the target's location, its speed, and its direction of travel. This information is fed into supercomputers. These computers then calculate the target's trajectory, predicting where it will be minutes from now. This prediction is what the system uses to plan the intercept. The third and most dynamic element is the interceptor missile. This is the bullet meant to hit the target. Based on the tracking data from the sensor network, the system's battle manager computer determines the optimal time and place to launch. The interceptor is fired. For the first part of its journey, it is guided by commands sent from the ground. These commands are based on the updated tracking data from the ground radars. The interceptor is put on a course that will take it to a general basket in space where the target is expected to be. But this is not enough for a direct hit. For that, the interceptor must take over and guide itself for the final, critical moments of its flight. The method of destruction is key. FEM-02 was designed as a hit-to-kill test. This is the most demanding type of intercept. It does not rely on an explosive warhead that detonates near the target. Instead, the interceptor, often called a kill vehicle, is designed to steer itself directly into the path of the incoming warhead. The combined closing speeds can be over 15,000 miles per hour. At that velocity, the sheer kinetic energy of the collision is enough to completely obliterate both the target and the interceptor. This requires an unbelievable level of precision. It is the equivalent of hitting a specific spot on a basketball from thousands of miles away, while that basketball is moving faster than a rifle bullet. Well, that's the scale of difficulty here. To truly grasp the test, we must look at the clock. The entire engagement, from the launch of the target to the moment of interception, unfolds over a matter of minutes. Every second is critical. Here is a simplified but precise timeline of the key events as they would occur in a successful FEM-02 test. At time 0, the target missile launches from its designated site. for example, the Kwajalein Atoll in the Marshall Islands. It climbs high above the atmosphere, its rocket engines burning for several minutes before shutting down. The re-entry vehicle separates. The re-entry vehicle continues on a ballistic trajectory toward a predetermined impact area in the ocean. This is the object the system must stop. Just a few minutes after launch, we reach time plus T1. This is the moment of detection. Far away, perhaps thousands of miles from the launch site, a powerful ground-based radar detects the target. Sea-based X-band radar, a land-based ANTPY-2 radar. Its computers immediately begin to track the object, distinguishing the re-entry vehicle from other pieces of debris. Spent rocket boosters, for example, are filtered out. The system analyzes the trajectory and confirms that it is a threat. This is a crucial decision point. Based on this data, the system's command and control battle management element must decide to engage. At time plus T2, the engagement order is given. The C2BMC system sends a command to a specific interceptor launch site, Vandenberg Space Force Base, California, Fort Greely, Alaska. At time plus T3, just moments after the command is received, the interceptor missile roars to life. It launches out of its underground silo, a 3-stage rocket booster, accelerating it toward space. Its initial flight path is calculated to place it in the right area of the sky at the right time. For the next several minutes, the interceptor is in constant communication with the ground, receiving updated tracking information on the target's position. The final, critical phase begins at time plus T4. High in the vacuum of space, the interceptor's booster rockets have done their job and fall away. The kill vehicle separates and is now flying on its own. It activates its own onboard seeker. This seeker, often using a sophisticated infrared sensor, begins to scan the cold, black backdrop of space for the heat signature of the target re-entry vehicle. At time plus T5, the seeker acquires the target and locks on. Now, the kill vehicle is in control. It fires its own tiny thrusters, making minute adjustments to its course. It fine-tunes its trajectory, ensuring a direct collision path. At time plus T6, the intercept happens. The kill vehicle and the target collide, resulting in a silent, brilliant flash of energy. Success or failure in a test like FEM-02 hinges entirely on the quality of the information the system receives. The sensors are the unsung heroes of missile defense. They must perform a series of difficult tasks with near-perfect reliability. The first task is detection. The system has to see the target missile as early as possible. Early detection provides more time for tracking, calculation, decision-making. This is why the radars used in missile defense are so massive and powerful. They are designed to peer over the horizon, spot a relatively small object traveling at hypersonic speeds from thousands of miles away. They cannot afford to miss it. Once the target is detected, the second task begins: tracking and discrimination. A ballistic missile launch does not just produce one object in the sky. It creates a cloud of debris, spent rocket stages, the deployment shroud, possibly even decoys designed to fool a defense system. The radar and its processing software must analyze the faint signals bouncing off all these objects. It must discriminate between the lethal re-entry vehicle and all the harmless clutter surrounding it. This is one of the most challenging aspects of missile defense. The system has to find the real threat in a threat cloud and maintain a solid track on it, ignoring everything else. The third task is to provide guidance data. The tracking data from the ground radars is used for two purposes. First, it is used to calculate a precise flight path for the target, predicting its future location. Second, this information is formatted into guidance commands and transmitted up to the interceptor missile while it is in its boost phase. This is called uplink communication. It ensures the interceptor is sent to the correct volume of space to begin its own search. The accuracy of this initial guidance is critical. If the interceptor is not put in the right place, its own seeker may not have a wide enough field of view to find the target. Finally, the sensors play a key role in the final moments of the engagement. The interceptor's own seeker is, in itself, a sophisticated sensor. In the case of FEM-02, this is likely an advanced infrared sensor, cryogenically cooled to be extremely sensitive to heat. As the kill vehicle closes in, this seeker provides the final, high-fidelity tracking data needed for a direct hit. It sees the target, tracks its movement, feeds this information to the kill vehicle's guidance computer. This computer then commands small divert thrusters to fire in short bursts, making the final, delicate adjustments to the trajectory. The entire process, from seeker activation to impact, happens in a matter of seconds. After the test is over, how do we know what really happened? The answer lies in collecting and analyzing data from multiple, independent sources. This is how engineers and officials prove, with confidence, whether the test was a success or a failure. One of the most important pieces of evidence comes from the ground-based radars. Radars monitor initial tracking and then continue to follow both vehicles throughout the flight. On radar, you'd see the target's track, and you'd see the interceptor's track. In a successful test, those two tracks converge to a single point in space and time. Then, at the predicted moment of intercept, the radar track for the target disappears. Another crucial source of proof is telemetry. Both the target missile and the interceptor are fitted with telemetry transmitters. These devices broadcast a constant stream of data back to the test range. That data is a running health and status report. Interceptor telemetry would show its systems were working correctly. It would confirm the kill vehicle separated from the booster. It would show the exact moment its seeker acquired and locked onto the target. It would also record the firing of its divert thrusters as it made final guidance corrections. In a successful hit, the telemetry stream from both the interceptor and the target would abruptly cease at the exact same moment. Optical sensors provide a third line of evidence. High-speed cameras record visible motion in great detail. Infrared telescopes capture heat signatures. These sensors are often mounted on aircraft or ships near the predicted intercept area. They're pointed at the patch of sky where the action is expected to happen. In a successful hit-to-kill intercept, these sensors would record a bright flash of light at the moment of impact. That flash is the collision's immense kinetic energy converted into heat and light. Powerful telescopes might then see a growing cloud of debris where there was once a single object. That visual evidence provides powerful intuitive confirmation of a successful intercept. The final proof comes from post-test analysis, where all these data sources are brought together. Analysts overlay the radar tracks, overlay the telemetry data, and overlay the optical recordings. They check timestamps and consistency across the systems. Did the radar tracks merge at the same time the telemetry streams cut out? Did that happen at the same location and time the optical sensors recorded a flash? If all the data from these independent systems tells the same story, the conclusion is robust. For FEM-02, success would mean the data clearly shows the target and interceptor tracks converging, telemetry from both cutting out simultaneously, and a corresponding flash of light, confirming the target was destroyed. It is important to remember that the purpose of a test like FEM-02 is not just to produce a success. The primary goal is to learn. Every flight test generates an enormous amount of invaluable data. Successful intercepts validate models. Failures generate forensic data. In a successful test, engineers validate their models. They confirm hardware performance. They confirm software performance. Under the extreme stress of a real flight, the data shows them what they got right. It gives them confidence in the system's performance. It allows them to refine their simulations, making future predictions more accurate. A success proves the concept and builds a foundation for improvements. However, a failure can often be even more instructive. When a test fails, the data becomes a forensic roadmap. Engineers trace the chain of events to the exact point of failure. Did the ground radar fail to maintain a solid track? Did the communication link to the interceptor drop out? Did the kill vehicle's seeker fail to acquire the target? Or did the divert thrusters not perform as expected? Telemetry answers these questions with precision. A failure gives a clear mandate for fixes. It uncovers hidden flaws not seen in lab simulations. If the seeker struggled to discriminate decoys, engineers develop more sophisticated algorithms. If a faulty valve caused the issue, that component is redesigned and ground tested. Lessons from one flight are incorporated into the next. Testing, failing, Learning, improving. Each test makes the system more robust and reliable. This process defines the system's limitations. No defense system is perfect. Understand the boundaries. Tests like FEM-02 characterize the performance envelope. They show what threats it is effective against. They show what threats it is not. Can it handle faster targets? Can it handle targets with advanced countermeasures? The data provides honest, fact-based answers. This lets planners and leaders understand true capabilities and make informed decisions about investments and strategy. Honesty about limits is a critical part of a credible defense. The knowledge gained from a single test like FEM-02 is a critical data point in the long and difficult journey of developing a trustworthy shield. In summary, the FEM-02 test was a highly structured event designed to challenge a missile defense system in a realistic scenario. The process followed a clear sequence. A target missile was launched to simulate a threat. A network of sensors detected and tracked that threat. An interceptor missile was fired to destroy it. The success of this mission was not a matter of opinion or speculation. It was determined by a careful, methodical analysis of the evidence. This evidence came from multiple independent sources. Radar systems, telemetry data transmitted from the missiles, optical sensors that watched the final engagement. Composite recap: radar, telemetry, optical, then wide ocean and sky. When all these sources tell a consistent story, the result is clear. In a successful FEM-02, the data would show the interceptor's track meeting the target's track, with both signals ceasing at the point of intersection, corroborated by a visual flash. A failure would be evident if the data showed the interceptor going off course, its seeker failing to lock on, or the two tracks simply passing by each other. Each test, whether a hit or a miss, serves a vital purpose. It provides a massive amount of data that engineers use to verify their designs, uncover hidden weaknesses, and make the system better for the next time. The process is a continuous cycle of flying, learning, improving. The knowledge gained from a single test like FEM-02 is a critical data point in the long and difficult journey of developing a trustworthy shield.